You're going to have 100 volts peak to peak RF. So from our mountain or our crest to our valley or our trough is 100 volts. So what's our distance from the DC offset to the peak? 50. Okay. So if we have a negative 10 volt center point or float, so if we have 50 minus 10, what's the voltage here? 40. And if we have negative 10 minus negative 50, we end up with negative 60. So that's what we mean when we have a 10 volt DC offset, negative 10 volt, with a 100 volt peak to peak from top to bottom. I could have also said a negative 10 volt DC offset with a 50 volt peak to zero voltage. Does that make sense? Okay, questions? Now, because I have two rod sets, I have the blue rod set and I have the red rod set. So whenever one set of rods is positive, the other set of rods is negative. They're always opposites. Okay, now, if we take our positively charged peptide, which rod set does it move near? The positive or the negative? The negative. So we're first going to go to the red rod set, then to the blue, then to the red, then to blue, to the red, to the blue. So if we look at these three-dimensionally and follow the ions, we see that our set of ions undergoes a circle. So if we're looking down the z-axis of the instrument, we're at the source, we're looking towards the trap, and we're traveling through the multipoles, the ions are doing this because of the RF. Okay, now, so we call that a circle. If we look at the instrument from lengthwise, our skimmer is always grounded at 0 volts. Our trap's always at negative 10 volts. Our poles gradually go downhill. So we might be 0 volts. The Q00 might be negative 3 volts. The Q0 might be negative 4 volts. The Q1 might be negative 5 volts. And the trap will be negative 10 volts. See how the ions roll downhill? So that's the DC offset. So the DC offset provides the forward motion. I go from 0. I'm a positive. I'm pulled forward by the negative 3. I'm pulled further forward by the negative 4 to the negative 5, and the trap pulls me in with negative 10.
Why don't you show the picture of the instrument and compare that?
Okay. So if we look at it back here, okay. So we start off at 0, and then we go down into Q00. We're pulled further down to Q0, a little bit more into Q1. And into the trap at negative 10. So it's the DC offset that provides the forward motion. So after doing a tune, you want to do a quick peek at your DC offsets and see if they make sense. What don't we want to see? You don't want to see bounce up and down. You don't want to see the ions come down and then have to come back up because they'll stall, they'll get stuck, and you'll lose them. Okay, does that make sense?
So you're going to show us where in the software we can look at it?
Yes, we're going to do a tune at some point and look at that. Does that make sense? Yes or no?
Yes. They don't understand. What don't you understand?
Now, I'm going to ask you consistently this week, do you understand yes or no? There's only two answers. One is yes. What does yes mean as an answer?
Understand it.
Understand it completely, okay? And when my advisor looks at me 10 minutes later, I can make some logical statement about what I said. What does no mean?
That means you can.
Everything else. That means from, what are we having for lunch today, to as close as, I'm not quite exactly sure. Now, I can tell when you're lying. When you say yes, and then your head does this. Okay, the slide is not going to come into focus by moving your head. So, yes or no, do we understand or do we have some questions?
No.
Could I repeat everything or was there certain parts? Okay. The skimmer is always at 0 volts. Okay. The trap is always at negative 10. The trap is what?
Why the trap is down this? Right.
So he's talking about the offset voltage for this oscillating RF.
Yeah, the trap is in the back end. Okay, so that's where the ions have to get to. That has to be the lowest voltage.
Along electrostatic.
I see.
Right, okay. So we want to go from 0 to negative 10, and we want to do it in a nice gradual downward slope. So our offset should go something lower than 0, and then this next offset should be lower yet, the third offset should be lower further, and then the trap is negative 10. So this guy should definitely be between 0 and negative 10, and lower than the previous two. Does that make sense?
Yes.
Okay.
Definitely helps to see the diagram.
Yeah, you want to understand that one. Okay, now.
So what do you do with these oscillations?
Okay, so the whole point is to take the ions and bring them into a circle. Okay, so that way we have control of them in the X and Y.
It's a beam. It makes a beam.
Okay, so you're right. The ions come through the skimmer. Okay, now they experience a problem. Our problem is my instrument has a set of small holes. The skimmer is a very small hole that keeps high vacuum from low. Then I have the next small hole, which is my inner multiple lens 0. That's another small hole to keep high vacuum from low. And then there's a third one, which is inner multiple lens 1, which keeps high vacuum.
So these are basically small holes that the ions have to look.
Right. Now, the problem is when an ion comes from high pressure through a small hole into low pressure, we experience the Venturi effect. Okay, the Venturi effect is basically the concept that makes every rocket engine work. What is on the back of every rocket engine?
Nozzle.
A nozzle. A nozzle is a small hole, okay, that takes high pressure gases and expands them out into low pressure. And what happens is we get what's called a supersonic expansion. The minute those ions come out of that little hole and there's low pressure, they go whoosh, which is why you ever notice the nozzle is kind of shaped. So that way that supersonic expansion is focused into a point and we get launching of the rocket. Well, we have that problem and we don't want that problem. The minute they come out through that small hole, we have this nice tight packet of ions and the packet goes whoosh, just like that. And if we don't refocus them, we're going to lose those ions.
They have to physically get to the next hole.
So the ions come out of that small hole, they supersonically expand into the opening of these multipoles. And what the multipoles do is they get these ions expanding and then they start getting them revolving into a circle. Okay, now, the RF causes the circle. The DC causes the forward motion. So my circle now becomes a cylinder, cone. Okay. The advantage that we have is we haven't pumped away all the gas yet. We still have a lot of background gas. Okay. So those ions undergo collisions. And when they collide with something, which would be like oxygen, nitrogen, air, they lose energy. And their circle gets smaller. So we use collisional cooling with background gas in an RF field to provide the circular motion with a negative DC offset to provide the forward motion, and we create a spiral that spirals in a very nice tight corkscrew and pops them through the next small hole.
So what is the helium? How does that help to focus it?
There's not the helium. There's not the helium. That's not the helium that you think of in the instrument. This is just the background gas that entered in the front end.
So
This is your mobile phase. Yep. Okay. Now, the cool thing is, as we come back further, we get less and less background gas, which means we get less and less cooling. But usually when they come through that first cooling, each pressure drop is a little less intense, so there's a little less of this supersonic expansion they have to control. So we go through the skimmer, and we refocus them in Q00. We go through inner multiple lens 0, we refocus them in Q0. We go through inner multiple lens 1, we refocus them in Q1. And then Q1 injects directly into... I'm going to kill your video before I'm done.
So this is basically a process to get the ions into forward vacuum.
Most efficiently.
There's a series of different pumps. Each area of the instrument is successively lowered.
Differential pumping. Okay, now, your instrument has two types of pumps you're going to see. The first one is mechanical pumps. I think you have 4 total, or 5. I always keep forgetting. There's 2 on the LTQ, And then there's 2 or 3 on the FT. Okay?